I shall now start presenting our team's entry into the Texas Instruments Analog Design Competition 2014 titled Hardware Implementation of Automated Wheel Drive Conversion for Electric Vehicles. Now, our model deals with the problems faced by the electric vehicles of this generation, which are two. One is the inability to navigate through all sorts of terrain, and second, conserving energy while doing so. Now, if you would care to come closer, you will notice what design we have employed. In the center is the MSP430 controller given to us by Texas Instruments. Now these are 12-volt relays which are used for switching on and off for the motors. These LEDs indicate the turning on or turning off of the front motors. And you can also see that we are using a resistor to sense the current which is flowing through the rear wheels. Now, the basic theme of our project involves the fact that when a DC motor is loaded, then the amount of current flowing through it increases. We are trying to map this current and finding out that which region is efficient for the functioning of the motors. And we are trying to keep all the motors at the same region of efficiency. Now, the advantage which we are bringing in is basically a two-wheel drive to four-wheel drive conversion and a four-wheel drive to two-wheel drive conversion. So, when the car negotiates with the slope, it turns from two-wheel drive to four-wheel drive, and when the slope is over, it turns from four-wheel drive to two-wheel drive. And by facilitating this, we are bringing in an energy conservation, because all the time, if there is, for example, two-wheel drive, then for the rear motors, the motors enter a region of inefficiency.
So as you can see here, the complete circuit can be majorly divided into two parts, the motor circuit and the relay charging coil circuit. The motor circuit involves the circuit which drives the motor, and it involves a 12-volt battery since the rated value of our motor is 12 volt. Then there's a resistor which is the sensing resistor, and it is only present in case of rear motors, not in case of front motors, since only the rear motor torque has to be sensed, the rear motor current. And then this is connected to the 12 volt PMDC motor. And in case of front circuit, there's a resistor and a LED in parallel to the motor to indicate the turning on of the motor in case of switching of the front motor. Then this is connected to the relay, which is the prime controller of our circuit. The relay consists of a front pin and a default pin and a non-default pin. So to explain the function of the relay, we have to move on to the relay charging coil circuit. The relay charging coil circuit consists of a relay connected to a 2N22 BJT, and the base of the BJT is connected to MSP, which controls the conductance of the BJT, and then this complete circuit is connected to 12-volt battery. So in general, the relay has a charging coil between these two pins and a circuit coil between the front, this third odd pin, and the back pin. So initially what happens is the charging coil, when MSP doesn't provide the pulse, this circuit is incomplete since BJT is not switched on. Hence the relay is not charged. And as the relay is not charged, the basic circuitry of the relay is this front pin is connected to this default pin, which is not in the circuit, and hence the whole circuit is switched off. But when we provide a high pulse from the MSP430, the BJT starts conducting, and hence this 12 volt reaches across these two charging coil circuit of the relay. As the relay gets charged, the circuit of the relay, this front pin, instead of being connected to this default pin, gets connected to the non-default pin, which is this, and hence this circuit also gets completed, and hence the front motor gets switched on. So this is how the switching action takes place in case of front motor.
What you can see here are the general characteristics of efficiency versus torque for a DC motor. Now, this band is the highest efficiency band for a given torque. And what we are trying to do is that when a car is on the plane surface, then we are only switching on two-wheel drive, so that we try to push it from 1 to region number 2 to make it more efficient, so that we extract as much as torque possible in order to reach this region of the DC motor to keep it in the highest efficiency. Now, if the torque requirement increases, then reaches the region number 3, and in that case, again, the efficiency reduces. So to deal with this, we switch it from two-wheel drive to four-wheel drive, and the torque gets shared amongst all the four motors, and it brings it to region number 2 for all of them, and this makes the entire car more efficient.
We are going to display the basic functionality of a four-wheel to two-wheel drive conversion car. When we switch on the power supply, this is a power supply rated of 32 volts and 12 amps. However, we will only be using 12 volts and 2 amps for our vehicle. When we switch it on, initially only the rear wheels will get the power and they will start rotating. But as we increase the load by rolling them through our hands, the front wheel will also get switched on, and the drive will convert from two-wheel to four-wheel drive.
I would also like to be able to notice that instantaneously when I switch on the power supply, the front motors will be activated for some time. This is because the torque requirement of the DC motor is initially high, and hence it has a high current requirement, which turns the front motors also on instantaneously. But once the torque demand reduces, again it will be switched off.
Now my friend will load the wheels. The indication of the light shows that the front motors are being activated, and it is only being activated just enough to compensate for the loading which is happening on the rear wheels, and hence it's blinking. Now we'll be negotiating with the track. We've built a track with inclinations of around 15 degrees, 10 degrees and 15 degrees respectively. And when the car will be started, you will notice that the initial torque requirement will make all the four motors activated at the same time. Then the front two motors will turn off, and only when it negotiates with the slope, the front motors will be turned on again, which will be indicated by the glowing of the red LED and the green LED.
We'll start the test run now. Initially the LED blew because of high torque requirement, and now they are switched off and the motor is running at constant speed. But when I load the rear wheel, the front wheel also gets switched on and the LED glows due to high torque requirement. When we remove the load, again the front wheel gets switched off. So this is the basic functionality of a vehicle, and now we'll try to depict it on a graph using processing. So initially the rear motors are only running, and hence there is a current requirement. But when we load it, there's an increase in torque requirement and thus the peak in the graph.
The following clip is the road test of our vehicle in our campus. The inclination is around 30 degrees and it is able to cover such a high inclination because of the road surface. And there is frequent switching. That is because of the fact that when the load is shared amongst the four wheels, again the load requirement, the torque requirement decreases, and because of this it switches off. But then since the inclination has not been covered, it is again switched on. Thank you for watching the demo of hardware implementation of automated wheel drive conversion for electric vehicles.